All right, so now we're ready to talk about area under the curve in dealing with parametric equations. And so we'll start off with a little bit of a review from Calc 1. We know that if y equals f of x, then the area under the curve on the interval AB would be the definite integral as you see here. Now, we'll take this a little bit further. We know that f of x is equal to y. So I'm going to change that to a y dx, and we're still a to b since we're technically a dx still in the function or on the integral. But now if we move a little bit further, and if we let x equal f of t and y equal g of t, then what we can say is that our area would be the integral where the y is going to be replaced with g of t, so g of t, and the dx needs to be replaced as well. Now, we know that dx dt is going to be f prime of t right here. So if we take the derivative with respect to t, that's going to be f prime of t. And if I move that dt over, then the dx is going to be f prime t dt. So I'm going to replace the dx right here with f prime of t dt. So f prime of t dt. And since our differential now is with respect to t, we're going to need different bounds, so maybe I'll just say t1 there and t2 there. So to figure out area under the curve, when given parametric equations, you can simply now refer back to this template where you have your g of t, which was your y, and your f prime of t, which would have been the derivative of the x function. All right, so let's take a look at a real quick example here, and we're just going to set this up so you can see how easy it would be. So if we have x equals 1 minus e to the t and y equals 2t plus 1, and we're interested in, let's say, 0 less than equal t less than equal 1, the area would be the integral from 0 to 1. That's what those are my bounds on my t, from 0 to 1. And then the g of t would be, in our case, remember g of t is going to be the y. So the g of t would be a 2t plus 1 multiplied by the f prime of t, and that would come from the derivative of the x coordinate, which in this case would be a negative e to the t. So a negative e to the t dt. So that would be your setup for an area computation like that. All right, so now we're ready to talk about arc length. And so we'll let x equal f of t and y equal g of t again. And I also want to go back and review a little bit of the Calc 1 stuff. For Calc 1, we defined arc length to be the integral from a to b of the square root of 1 plus dy dx squared dx. Now clearly we're going to want to be with respect to t, so let's make some changes here in notation. So I'm going to go t1 to t2, and this is going to be a square root now of 1 plus. I'm going to change it up a bit. We know that the derivative of y would need to be with respect to t, so g prime of t, and then on the bottom we would have f prime of t squared, and our dx we talked about a moment ago is f prime of t dt. So again, all I did is I changed from x's into t's, t1 to t2. The derivative of y would be g prime, the derivative of x would be f prime, and the dx, as we talked about a moment ago, goes into f prime of t dt. All right, so now a little bit of algebra here to clean this up. So t1 to t2, and then we're going to have f prime of t squared plus g prime of t squared all over f prime of t squared with an f prime of t dt. So I just created an LCD here and combined these two terms. Then I'm going to go ahead and separately now view this as a radical in the numerator and a radical in the denominator. And you can see in the denominator, the square root and the squared would go away, leaving us with just, in the denominator, this f prime of t. So the f prime of t there and there would go away, leaving us now with what our final formula is going to look like. We're going to have this f prime of t squared plus g prime of t squared and our dt hanging out there at the end. So here's an arc length formula now for having been given parametric curves instead of your normal x and y equations. All right, so we'll take a look at an example, and you'll see getting it set up is really the only new part of this. So I would recommend for a problem like this, just like in Calc 1, to organize your work as best as you can. So we'll go ahead and we'll start here, clearly needing an x prime, which would be our f prime in this case. So x prime would be 2 over the square root of 1 minus t squared, and y prime would be our negative 2t over 1 minus t squared. So remember how we defined them earlier was that this was your f of t and this was your g of t. So x prime and y prime I'm just using for notation's sake. All right, so then I'll go ahead and I will square both of these. And so in doing so, that's going to give us a 4 over 1 minus t squared. And then this is going to give us a 4t squared over 1 minus t squared squared. And then it looks like I'll need to add these two things together. So when I add those together, now I'll create an LCD, and I'll have 4 over 1 minus t squared squared. And then finally, I'll have my square root over the top of it, leaving me with 2 over 1 minus t squared. So again, all I've done so far is identified this as my f of t, this is my g of t, so therefore this would be my f prime of t, and this would be my g prime of t. Went ahead, worked through the formula, found the derivatives, squared them, added them together, and then square rooted, leaving me with this at the bottom. So to actually figure this thing out, we would integrate from 0 to 1/2. The 0 to 1/2 comes from right here, and I can't forget my dt. So there you have it. Again, not anything very different. It is a different formula though because we're given information in a different manner, but in order to put it all together, it's pretty much the same as what you've seen many times in the past. All right, so I'll briefly introduce then the idea of surface area of revolution, which is just a little bit of a step beyond arc length. If you remember from Calc 1, we defined surface area of revolution as that circumference multiplied by the arc length. So this was the Calc 1 arc length formula. This was our circumference given we're going around the x-axis. So now if we kind of rewrite this or reformulate this given the parametric equations x equals f of t and y equals g of t, we'll see that our surface area now is going to be an integral from t1 to t2, and we'll still have our 2 pi. We also know that from Calc 1, y equaled f of x, and so all I'm going to need to do now is drop the y value g of t right there. So that's going to be a g of t, and then multiplied by the arc length component now given the parametric equations. So that would be our f prime of t squared plus g prime of t squared followed by our dt. So again, nothing really crazy there. The arc length, I just went ahead and rewrote the new one we came up with a moment ago. The f of x, which we know is equal to y, where we know y is equal to g of t, I replaced right there. And so there's your arc length, or excuse me, the surface area of revolution formula, once again going around the x-axis. If we want to go around the y-axis, let's say, we'll go t1 to t2, and then we'll have our 2 pi f of t followed by that same arc length, f prime t squared plus g prime of t squared dt. And that's the y-axis in that case. So again, these formulas are what they are. You can certainly work through these on your own. There's no doubt that you'll be able to put everything together that you need. It's just important to see where they come from at this stage of the game.